Kraft, he said that the particular solution is expressed like, I think he used t, like d sine omega t, d sine omega t, which means he said that the particular solution of this system due to this external load is just d sine omega t without a cosine component. Later, we'll see that this t will become 0 for p0 sine omega t. But in my opinion, it's better to write this complete form. There's four expressions, like c sine omega t plus d cosine omega t. Although the t will become 0 later, because this is the general form. And later, when we discuss about system with damping, you will have advantage by using this form. Of course, this is correct. This is correct. D sine omega t or c sine omega t without cosine part. It's correct. And the same meaning if you have a p0 cosine omega t, because we only give you the p sine or sine p0 sine omega t result here in the class. But for p0 cosine omega t, if you use the same thing, of course, this part will become 0 and t will remains. Okay, so this is a slight difference between the slides and the textbook. So this is a particular solution. The particular solution in response due to p0 sine omega t. So we have this form. Okay, we have this form. And now we need to determine C and D. So because this is the form of the particular solution, so we can use two dots. So one dot you got C omega cosine omega t, t minus t omega sine omega t, we see for velocity. And then acceleration, you got acceleration. Then you bring acceleration here. You bring this this is displacement here. Okay, you got the expressions. And then you rearrange everything, the things along with the sine omega t, the part, this part, and the thing along with cosine omega t. So you put these things together and moves all the samples or the variables to the left side of the equation. And here is 0. Okay, here is 0. And because this equation, it satisfies or it stands at any time instant, which means this one will not be 0 or this one will not 0, always 0. So to make this equation to be satisfied for any time instant, you need this part to be 0. Okay, this part to be 0, this part be 0. Okay, and this part is 0. This is a condition that this equation stands for any time instant, right? So by using this, I mean, this part equals to 0, you can get C equals to P0 divided by K minus M omega squared, right? It's P0, I don't, just quickly write this, omega squared M. Then this part became 0, you know, D equals to 0. D equals to 0. So we got D equal and C equal. And if we move K out, so you simplify this. Cancel this. So P0 over K, you move K out here. So P0 over K is the static deformation. Right, you have load whose amplitude is P0 and applied to a system whose stiffness is K. Then this part will be a static deformation, right? Static deformation. And because you move K out, so here became 1, and then this one divided by K, and K is M omega n squared, right? M omega n squared. Later, I will not give you so detailed information about every equations. This one just gave you example. So K equals to M omega n squared. So the M will be canceled. And then omega divided by omega n. then square. So this is C. So this is C. And this part, in many textbooks, they use a new sample, which is beta, the frequency ratio. This is external frequency divided by natural frequency. So we call this is frequency ratio. And use this sample beta to express this. So this is the beta. So this is beta. And this is we call CND. Then we can solve the complete solution because we know the complementary solution form. We already know the particular solution. We have one particular solution. Okay, one particular solution here. So this is the complementary solution. So we have the total solution or complete solution. And here we introduce initial conditions to determine A and B. Okay, you cannot directly use A, B for free vibration because this is only for complementary case. Here we have external load here, so you need to determine the AB after you apply this. This is from mathematical requirements. So after we introduce the initial conditions, so U0, which is U0 at time instant t, so you can quickly get this part equals to 0, right? Because sine omega is 0. So this part became 0, and this part became 0. And this is 1 equals to U0. So A equals to U0, which is initial displacement. And similarly, you can get the B is like this. Okay, the B is like this. So you got A and B. So the final solution of SDF system without damping under harmonic P0 sine omega t harmonic excitation is like this. So this is a total solution or final solution. So you can see that there are two parts for this final solution, two parts. The first part in red, is you can see that the frequency of the first part is the natural frequency of the system, which means this part, it vibrates at the frequency, at the natural frequency of the system. And this part, you see sine omega t, this is omega nt here. And this part, it is vibrates at the frequency of the external load. So this is a natural frequency part, and this is the external load frequency part. And we call this part in red, we call it transient response. Okay, transient response. And this part we call it steady state response. Okay, steady state response. The transient response, because if there's damping, because for real structure is always damping there. Later we'll see there's a damping part here. So this part will dash out because of the damping, which means the amplitude of this part will become small and small, quickly, very quickly. So means dashed out. So that's why it's called transient response. And the second part, which is the frequency is the same as external load. As long as the external load is there, and this part will remain, right? Because you have the external load there applied to the structure. Then as long as the external load, harmonic sine omega t, the harmonic loading is there, this part will remain. So we call steady state response. Okay, steady state response. Later, when there is damping, we usually consider this part, and this part we don't care. In many cases, we don't care about this part, and because there's here in current discussion, we don't have damping. The system doesn't have damping, so this part we need to consider it. So this is a total response, two parts. So this is as if you remember, this is our first term today, which is a transient response. What's the meaning of transient response? What's the meaning of steady state response? Steady state response. So here's the question. If the system starts at rest, which means the initial velocity and initial displacement are both zero. Then start from here, we apply sine omega t external load to the system. Is there transient vibration or not? I mean, if we have, you see, we have a SDF system, which is at rest. There's no initial displacement, no initial velocity. Then we apply a harmonic loading at the time instant zero. We start from zero, okay? Then the structure start vibrate, okay, start vibrate. So my question is, at this case, with all these conditions, is there the transient vibration?
No.
Anyone?
No.
Any different answer?
So there will be transient vibration.
So we have different opinions. One say no, one say yes. You can see here. You can see here. Okay. So if this part is zero, which means the initial displacement is zero. Okay, this part zero, this part zero, and the initial velocity is zero. This part is zero, but we still have this part. If there's no damping, okay, this part, and this part, it vibrates at the natural frequency of the system. Okay, natural frequency of the system, which means even the structure was excited at rest with no initial displacement, with no initial velocity, its vibration, its total vibration still have the component of transient response. Okay, so we still have this part. We still have the transient response part, even though the structure starts at rest. You can see here. You can see here. So this is the thing about this static response, which means even the initial condition is zero. The fact that the excitation is suddenly, when the excitation is suddenly applied and times zero, still it will result in a response that consists of a transient part and a steady part. A transient part and steady part. The two parts still exist. So to summarize that, the transient part, transient response, we call it the vibration at the natural frequency of the structure itself. When there's damping, this part will be dashed out or damped out, which will disappear with the time. And the steady state response, vibration at the circular frequency of external load, we call this part steady state response. Actually, you have this experience in your daily life. So anyone have experience driving a car? Yes, this part. I mean, probably the red part here. You can see at the very beginning is 1, which means when the beta is the frequency ratio is equals to 0, and this part becomes 1. Okay, becomes 1. And when the frequency of external load is very, very close to the natural frequency of the system, of the structure, this part becomes very, very large. Okay, very large. And if this is 1, actually this part will becomes infinite. Okay, because infinite. And of course here the negative part is the same. So, and you can see this part is interesting. We'll discuss later. So here we introduce a so-called dynamic displacement response amplification factors. You see, this is the steady state response of the system due to a harmonic loading, and this is its amplitude. Okay, this is amplitude because this is sine omega t. This is amplitude. This is amplitude of the dynamic loading of the steady state response, not the loading. So this is the amplitude. And we know that the maximum static deformation P0 over K, which means this part is static deformation. And this is amplitude, which means this part is like a factor applied to this to the static deformation. And so we define this as a displacement response amplification factor. We use the absolute value here, so absolute value. And this is U0, this is amplitude divided by UST, static loading. So this one is called displacement response amplification factors, which means if you know the static deformation and you know this factor, then you can directly know the maximum value or maximum amplitude of the steady state response. So steady state response. So here comes the second important term today. This one, we call it amplification factor for displacement. Okay, amplification factor for displacement. So if we introduce this new sample here, RD, because we have, you see we have absolute value here. So to balance this two, we need a new phase angle here, the minus here, this is phi, and then the phi should be 0 when omega is less than omega n, and or it should be pi, or 180 degrees, when omega larger than omega n, or omega larger than omega n. So this is the amplification factor, so amplification factors. Again, when we plot this is the RD curve, amplification factor. This is RD curve, and this is the value, the change, the variation of this value along with this line. This is the frequency ratio. Okay, this is the beta. Okay, this is beta. This is phase angle. This is the phi. So, and this is beta. So you can see that the variation of RD with beta and the variation of phi with beta, the phase angle with beta. These two curves are very, very, very important, especially when we discuss about later with damping, the system with damping. But now we can first discuss the system without damping, this curve. You can see the curve when the frequency becomes larger, then the RD becomes larger, which means the factor, because this is amplification factor, so it becomes large. It becomes larger. And when the omega equals to omega n, 1 equals to omega n, which is resonance, third term today, resonance here, and this one becomes infinite, which means the dynamic loading one becomes infinite compared to the static load if there's no damping. And with increase of this one, then the RD with increase of omega, because it's a ratio, with the increase of the omega, the RD becomes smaller, reduced. This increase then becomes the maximum, infinite actually here, then decrease, okay, decrease. So after this value, so after this point, which means after a certain value of ratio here, what is the ratio? You can imagine, you can guess what is this value. So after this value, which means when the frequency of external load is larger than certain value, the dynamic load, the RD value was less than 1. Less than 1 means the dynamic deformation is less than the static deformation. Okay, less. And with increase of the omega, and the RD became smaller and smaller and smaller, smaller and smaller. So anyone give me an idea what is this value? What is this beta? What is this beta?
1.5.
What?
1.5.
Sophia gave you this equation already. So you need to determine this value, right? So it should be equals to 1. You write this. So one solution is this became zero. This is one solution, which is this part, right? This part, this point. But this is meaningless. Because this is static deformation. Because omega equals to zero means there's no loading, no dynamic loading. It's a static loading. So no dynamic loading. So this is one solution for beta. So the other one should be square 2, right? Root of this one. Okay, this is this one, this point. The first point is equals to 0 because this one RD equals to 1. You see here, 1, RT equals to 1. Which means when the beta is larger than this value, the RD will smaller than 1. Smaller than 1. So this gives you many interesting things when you design a structure. Design a structure subjected to harmonic loading. This curve, this so-called dynamic amplification factor curve. This is very important. Okay, very important. So as I mentioned, I think I mentioned this because omega equals 0 here. It's actually a static load because there's no period, no frequency. So this one must be equals to 0. Must equals to 1. Okay, when the frequency is very high, you can do an experiment by yourself. If you have a pendulum, okay, the pendulum is actually a single degree of freedom system. Let me see if I have anything to simulate a pendulum here. So if you have the pendulum, you move the end of the pendulum, which is the movement of the support. The movement of the support is actually a loading, and you can simulate harmonic loading. So when you move very slowly, very slowly, you try to find something here to simulate this. So you can see we have a charger here, which like we have a head down here, right? Down here. So this is a pendulum. Okay, this is a pendulum. I think you already have the homework to derive the equation of motion for this pendulum. And then you can move. This is a so-called free vibration, right? We have initial displacement. Or you can move the support here, like at my left hand. You move the support. The support is like movement of the support is also a dynamic load. We already know this, right? So if you move very slow, which means the external load is very small, very slow. See, very slow. The dynamic loading is the same as the static load, almost the same. So RD equals to 1. And when it moves at resonance case, I try. See, it becomes larger and larger and larger. If there's no damping, because this system has damping, so it cannot become infinite. And if you move very quick, the left hand moves very quick, I'll try. The system doesn't have time to respond, so the RD becomes very small. So there's no dynamic loading, no dynamic deformation. I'll try. No, a bad example. So you can see when it moves very quick, very quick, which means omega is very high. Then the RD becomes very small because the system doesn't have time to respond. So this is a physical explanation why we have these features for the RD curve. So at the resonance case, when omega equals to omega n is resonance, in theory, theoretically, the RD will become infinite for non-damping system, And because in this case, the particular solution, if we still use this form, let me go back. One minute, further. See here. So you see, if omega equals to omega n here, omega n here, as a resonance case, omega n, you can see the complementary solution will be the same form as the particular solution. because this is not attainable. This is not allowed by the mathematical theory. We need to change the form for the particular solution, because this one, at this case, the two became the same form. They have the same form. So we need to change the form for the particular solution. We need to use a different particular solution. Otherwise, we become the same. So this is from mathematical theory. Then this is at the resonance case, and turn to here. So at the resonance case, we change the particular solution like this: CT cosine omega nt, because here omega equals to omega n. So we use omega nt here. So CT, C, this is unknown coefficient, CT times cosine omega nt. This is particular solution. And this is omega n equals to omega equals to omega n. Then we use this plus the so-called A cosine omega nt, the complementary solution. Okay, cosine omega nt plus B sine omega nt, sine omega nt. Okay, so I need a mouse later. Better for drawing. And then you can introduce the initial conditions. You can determine A and B again. You can determine A and B again. Then we can have the final solution like this. So like this. This is for the resonance case. Okay, resonance case. We can have the solution for the resonance case. Okay. So when we have the resonance case, we can plot it. You can plot you can see this is what happens when the external frequency, the frequency of external load is same as the structure. So you can see the solid line is the response of the structure. The solid line is the response of the structure. And you can see with the increase of the time, the amplitude of the vibration becomes larger and larger and larger. But it's not becomes infinite. It takes time to build up the amplitude. It's not became infinite at very short time. It takes time to do this. It takes time to do this. You can see we call this build up. Okay, build up. It takes certain times to do this. And at some cases, very rare cases, when the omega, the external load, the frequency of external load is approximate to omega n, not equal, but very close, very, very close. Then you will have this phenomena we call bitting phenomena. Okay, bitting phenomena, which means the transient and steady state response, they sometimes add together or they sometimes cancel each other. Okay, during the break, I wrote a MATLAB script to show you this bitting phenomena. This is very common in field test. So when you change the frequency of the shaker very close to the natural frequency of the system, we will have this bitting phenomenon. Okay, which give you a sign that the frequency is very close to the natural frequency of the system. So the building up phenomena up here. So let me summarize this. This is an important thing called dynamic amplification factor, and this is for non-damping case. And then we will discuss about the system with viscous damping. So viscous damping and how it responds to this P0 sine omega t loading, respond to this harmonic loading. So any questions so far? So we have 2 minutes for the break.
So does it mean that if, for example, we want to avoid the high dynamic response, can we just be playing with the frequency, natural frequency of the structure, for example, like to avoid resonance, right?
You mean change the natural frequency of the system to avoid resonance?
Yeah. For example, yeah. Can
Yeah,
you
this
just
is idea. This is idea. I mean, in my opinion, the whole structural dynamics, at least what we have learned here, is about how to use resonance and how to avoid resonance. And this is one way. When you design a structure, let's say we know the loading here, like wind or earthquake, the dominant frequency of the wind, let's say is 1 second. And if you design a structure, you have a structure plan whose period is nearly 1 second, it's dangerous. So you need to change the properties, the dimension of the structure, or even the height of the structure, that like making the natural frequency or natural period of the structure to be away from the 1 second, which will be a safer design. Is that your question?
yeah. Thank you.
So we call frequency turning, which means you change the frequency or you turn the frequency of the structure away from the dangerous range, the dangerous range of the loading, of the external loading. So you change the design, then the frequency in the period of the structure will be changed and away, became away from the dangerous range. Okay, we have 10 minutes break. Okay, 10 minutes break. We will have the second one at 9:45. 9:45. Let me switch off his mic. Okay. One more. Okay. Then you bring the things here, and after you rearrange this equation by put the things with along with the sine wave d together with cosine wave d together like this. So again, we know that this part should be 0 and this part should be 0 because this equation stands for anytime instance. So you got this one equals to 0 and this one equals to 0. And you have two unknown coefficients, one is c, one is d. You have two equations, and you can solve that. You can get the expressions for c and d. So this is what we get from the previous equation. And by solving this two equations simultaneously, you can get c like this and d like this. And if you use the beta, so it will be a simplified form, like 1 minus beta squared, like the things you can also use beta here. So this is for C and D. And now we have the total or complex the expression for the two coefficients here, A and B, we should introduce initial condition to this equation. Initial t equals to 0 give you initial displacement, and then you can also have the initial velocity, and you can get E and B. You can do this, okay? You can do, but very few textbook will give you the final expression for A and B, because it's not very important. Because in this case, there's damping. This part, you can see this is transient part, because it vibrates at the natural frequency of the system. It's a damped natural frequency of the system. And this part vibrates at the frequency of the external load. So this is the steady state response, it's a transient response. Because you have this part here, damping. So this transient response will be dashed out quickly. So we only, in most cases, we only focus on this part. So very few book will give you the expression for A and B. And you can do this, you can give A and D by introducing initial conditions here. And you already know C and D, you can have the expression for A and B. So I just gave you the reason why our textbook doesn't give you the expressions for A and B. This is another explanation why this. You can see this solid line, this one, solid line, is the total response. Consists of two parts, transient static, and this part, the dashed line here, is steady state response. The second part, okay, the second part of this response. Let me go back. So this part, okay, this part is the second part. And you can see after several cycle of vibration, so this is a T over period. So you can see after several vibrations, the total response will became very close to the steady state response because the transient one will be dashed out. So that's the reason why we usually only consider about steady state response. But here is a question: when, at what time, and what situation you must consider transient response? Can anyone give me an answer or give me a case? At what condition or when you must consider a transient response? Okay.
The damping value is so that damping takes place so long period for long. When damping takes long time, so we have to consider the transient response according to the e power minus I omega t.
Mm-hmm. Okay, I think you give me the right answer because of the time, which means because the steady state response, they need time for the transient part to be dashed out. If the external load is very short, the duration is not very long. I mean the external load. In that case, you must consider about the transient response because the total response they will have they don't have a very long time. They don't have enough time to dash out this one. And you can see here, in many cases, the maximum value what happens if you consider the steady state, the total response with the transient response being included. A clear example is earthquakes. You see, you have a structure subjected to earthquakes. You have a structure, then you have earthquakes here. It's like this, the earthquakes attack these structures because the duration of the earthquakes. Of course, here we give you the loading side harmonic one, but I just show you this example. If the duration of the earthquake is very short, usually is short. The earthquake is about, especially the moon part, with a high energy. This is about 30 seconds or 20 seconds, 20 to 30 seconds. So it's very short. So in this case, you need to consider the total response of the structure. You cannot just consider about the steady state response with steady state response. So in this case, you cannot ignore this, the so-called transient response. And why in many textbooks it's always said we only consider about the steady state response. One reason is that historically, the structural dynamic is the source of the structural dynamic is for mechanical engineering. Okay, mechanical engineering. You have a machine, running machine there. Then this is subjected to a harmonic loading. And for the mechanical things or for the machine, they always runs for a very long time. Like you start a machine, start engine, usually the engine will runs for a very long time. And because the excitation, the time of excitation is very long, so they usually only consider the transient or steady state response. They don't consider all the transient. But in civil engineering, like I just mentioned, the earthquakes, or you have impact loading, which happens in a very short duration. You must consider the total response. You must consider the total response. And later we will study the numerical method for solving the equation of motion. And in numerical method, it gives you directly the total response. It gives you directly total response. So you don't need to worry about which is the transient, which is the static, because it gives you the total response. But here, for the harmonic loading, later we discuss only about the static state response. Okay, so you should be aware of this. You should be very, very clear about this. Therefore, you need to understand some reference papers or textbooks. They always say that from this moment or from here, start from here, we only consider the steady state response of the structure. So, which means they ignore the transit part. But you need to judge by yourself whether this assumption is correct or right, correct or wrong. Okay, correct or wrong. So this is one thing. Okay, at the resonance case, because here we don't need a different form because the complementary solution is different. They have different form as a particular solution because you have exponential things outside the sine or cosine part. So they have different form. So here we can use directly the same form, like C sine omega t plus D cosine omega t. And we already know the CD expression of CD is here. This is beta. And because now here, the omega equals to omega n, so this one becomes 1, and C becomes 0, because this one becomes 0. And you can simplify this. This one is 0, okay, this one is 0, and this is 1, this is 1, and this is 1, this is 1. So the D became this value, minus UST divided by 2 zeta. So this is resonance case. At resonance case, we have the values for C and D like this. And here you know the total response, like this, right? The total response is like, at resonance case like this. And because here the CD expression is simple, is simple for the particular solution. And for this case, you can solve the A and B value. Okay, just now I said, because for normal case, omega not equals to omega, and you have C and D here. You can introduce initial condition to get A and B, which is very complex. You can by yourself. But so we don't give you that expressions. But in this case, because you can see the expression of this part is very simple. So we can get A and B by introducing initial conditions. And you can get A like this, B like this. Okay, A and B like this. So this is the value for A, B. And if we put all these things together, we can see UST divided by 2 zeta and this part. And if you draw the plot, so the solid line is the response of the SDF system under harmonic loading as a resonance case. You can see similarly the amplitude of vibration increase with the increase of time, but it has a boundary. Okay, it has a boundary here. It's a limitation, which the limitation is 1 divided by 2 zeta. So pi divided by 2 zeta. So this is the static deformation. Okay, the static deformation. So you can see the amplitude, the maximum value should be 1 divided by 2 zeta times UST. So if the damping is 0.01, which is also very common, and the UST will times how many? 50 times. Which means if you have 1 meter, let's just say 1 meter static loading, static deformation, and the loading becomes dynamic load, and it's a resonance case. And the dynamic deformation, the maximum dynamic deformation will be 50 times larger than the UST, than static load. So that's why resonance is very dangerous for structures. So we need to pay more attention to this case, to avoid this or to use this. As I just mentioned, that in my opinion, the structural dynamics here is mainly about how to avoid resonance and how to use resonance. Here's the example. You see, here's a person standing on this bridge. and play this video. Oh. So standing on the bridge. Standing on the bridge means a static load. A static load. I need the pen again. So it's like a bridge. You have a bridge. You have a person standing on the bridge, on the middle of the bridge. Okay. Here it's a P0. It's a static load. It will generate some deformation of the bridge, which is delta ST, which is static load, static deformation. Okay, static deformation. And the static deformation is very, very small, right? Because the weight of the person against compared to the weight of the structure or the stiffness of the structure is very small. And now, if it became like sine omega t, P0 sine omega t, sine omega, let's see, too difficult for me. P0 sine omega t. Then apply to the same structure. And you have a dynamic load, okay, which is U. Let's use U0, use this symbol. It will be very large, many times of the delta ST, depends on the damping. For the bridge, the damping is already very small. So that's why this amplitude is the same, P0, but it became a dynamic one, okay, it became a dynamic one. So you can see, let's see the, to cancel this pen. Okay, let's play the reading. You can see very clear vibration of the bridge. Okay? Very, very clear. You can, by eye observation, you can see very, very huge, very significant vibration amplitude of the bridge due to the dynamic load. But if a person is standing here, static one, it don't have a very significant deformation. So this is, you can compare static deformation, dynamic one, and resonance. That's why it's very dangerous. And we can see the effect of the damping. Okay, if influence of the damping. You see, this one is 0.1, 0.05, 10%, 5%, 1%. You can see as a resonance case, the increase of the amplitude at different damping values. It's like this, the influence of the damping. The lighter the damping is the lighter the damping, larger is the number of the cycles required to reach a certain percentage of displacement U0, which means because you have a steady state response, okay, steady state response. When you start the vibration, you apply a dynamic load to the structure, and the structure starts vibrates, okay, vibrates, and it finally reach the steady state response. If we like to know how many cycles we need, let's see the what, because it takes time to build up, you see here, takes time to build up the amplitude. So we want to know how many cycles, how long it takes. The vibration amplitude can reach, let's say, 90% of the final U0. Okay, final U0, which means we can see it's already reached its steady state response. So if the damping is small, it takes longer time. It's like this. For smaller damping, it takes longer time to reach this ratio. This is what the figure tells you. Okay, you can actually use this equation to solve this. Like, I draw this very badly, but I can just simply show you this. This one is like 1%. The damping, it takes 40 cycles. 40 cycles. So how long is like 40 cycles times t, times the period, times t, is how long it takes. What's the use? What's the usage? What's the application of this curve? This is from my personal research topic. We're studying the response of floor. This is the floor subjected to human walking or human jumping load. Okay, jumping load. One person who is jumping here, okay, jump up and down is jumping here. So we have these experiments. So this is one of my students, PhD students. She she asked me how long I need to jump on this floor. Because I asked her to jump on this floor to generate vibration of the floor, to simulate one case, like people jumping on the floor, what is the response of the floor. And she always asked me how long I need to jump, 1 minute or 30 seconds? So actually we use this curve to determine this. For example, if we know this the damping of the floor is like 2%, and I like the amplitude, which means the amplitude to be 95% of the final target. That's U0, and then you can see you need 30 cycles. Okay, 30 cycles, and 30 cycles times the period of the floor, and times the period of the floor. Then we know how long it takes. How long it takes for you to jump. Actually, I think I asked her to jump 1.5 minutes. Actually, it only needs one minute. But to be safety, I asked her to jump 1.5 minutes. Okay. So this is the one example showing you how to use. What is the usage of this idea? Okay, let's summarize this. Again, we have this dynamic amplification factor. To summarize these expressions, we know the particular solution is like this, or the steady state response. We don't consider a transient response. Or in another form, it can be U0 sine omega t minus phi. Okay, minus phi. And this is amplitude. Amplitude should be CD square out, square root. And we have U0, and this is phi, the phase angle. We'll discuss this later. And the expression for this U0 should be like this, and then this is the phase angle phi here. And by this, we can introduce again the dynamic amplification factors for displacement. U0 divided by UST, and U0 is like this. So this part is RD, is the amplification factors. So this part is amplification factors, RD. So it's similar like the undamping case. Undamping case is like, if you still remember, it's like 1 minus beta square, then that's absolute value. So this part, because no damping. And this is with damping case. RD is like this. And we also can have velocity factors and acceleration factors. I will not give you the detail, just give you the expressions. If you have questions, you can ask later to explain these two factors. For now, you just know this is beta, which means RD times beta equals to RV. This is for velocity, and this is for acceleration. So beta squared, then times RD equals to RE. Again, let's discuss about the variation of the amplification factor with frequency ratio and damping ratio, because it depends both on two factors. One is the frequency ratio here, and the other is the damping ratio here. So this is for the curve. And you can see this one is 0.10%, 0.1. This is damping ratio 0.1. And this one is 0.2. And this green line, 0.5. And this one is very interesting. This is 1 divided by square root of 2, square root of 2. And this one is 1 point. This damping ratio 1. Okay? So this is the variation of the RD curve with frequency and with damping. So again, this curve is very important for you to understanding the behavior of SCR system subjected to dynamic loading, harmonic loading. So this is very important curve. So you can see if generally with the increase of the damping ratio, so this is a smaller one, the larger, the largest. So with the increase of the damping, generally RT will become smaller. Okay, this is what we can first observe from this curve. We can observe from this curve. With the increase of damping, the RT decrease. So this is one thing. And if the damping is larger than a special value, for instance, it's larger than this, we can prove this. Why is this value? This curve? Is this curve? When the damping ratio is larger than this value, the RT is always smaller than 1. Which means if the damping ratio of the system is larger, then the dynamic amplification, the dynamic deformation is always less than the static deformation. So the static deformation. So this is another observation. And the third one is that where is the peak? Where is the peak of this curve? So where is the peak? Is the peak at this value? The peak means the maximum value of RT, the maximum value of RT. My question is the maximum value of RT happens at beta equals to 0, equals to 1? Is that this point or not? Can I enlarge this and try if I can enlarge this curve? So, sure. You can see, if you look clearly to this curve, let's see this curve, the peak happens here. The peak, the maximum value, the peak happens here, about here, and this point, yes, less than 1. This point is omega equals to omega, or omega n, which means the maximum value of RT happens at frequency lower than omega n, lower than omega. But you see the damping ratio here is 0.1, and this is very close. The two is very close. Although they're not the same, they're very close. And this is very high damping ratio for civil structure. If you have another damping ratio which is smaller than 10%, maybe here, forgive me, my bad, right drawing here. So the 2 points will be very close, but they're not a different one. They're not different. Let me repeat this. We have omega equals to omega 1. Omega, this one. Omega equals to omega 1. This is resonance case. When we say resonance case, we mean omega equals to omega 1, okay? But actually the maximum value, this one is very clear. You can see the maximum value happens at here. And this one is the omega equals to omega. Omega equals to omega. So it happens at a different damping ratio, a different frequency ratio, which is smaller. So that's actually this observation. So one is the factor decrease with increase of damping, and the damping had much significant effect around the resonance zone. Let me go back. This is also a very important observation. Let me cancel all these drawings. You can see the damping, the effect of damping is very significant at this part, at the so-called resonance part. And at this part, and also at this part, it's not significant. It's not significant. The effect of damping. This is also very useful. Let me give you an example. If you have a dynamic load applied to this structure you're going to design, and you know the frequency of the structure is very is larger than the natural frequency of the system. And now, as a designer, you are asked to reduce the dynamic deformation of the structure subjected to this loading. So my question is, can you increase damping of the system to reduce this dynamic deformation? Is this an effective way or not?
No, I think no.
No, because when the omega, you can see here, when the omega very large than omega n, here you can see omega, this part means omega larger than omega n, or far larger than omega n. And you can see that the damping ratio, they almost have no effects. Although you have already 10 times larger damping, this is 0.1%, this is 1, then 100%. So this is already 10 times larger, but you can see the RD almost doesn't change, or almost the same. Which means at this situation, if you increase the damping of the system, it will not be an effective way to reduce the deformation of the system. And as this part, if your situation is like this, is very close. It is very close to the omega n, and you are asked to reduce the deformation, dynamic deformation of the system. You can see here, increase of the damping will be very, very useful, very, very significant. So as a so-called resonance situation, a resonance case. So this is the second observation. So the damping have much significant effect around the resonance zone. And when we see resonance, we see the omega equals to omega n. At that time, the dynamic amplification factor equals to 1 divided by 2 zeta. Okay, this is a very useful conclusion. So it's 1 divided by 2 zeta. One frequency equals to omega n. And the second part is the maximal DMF doesn't occur at beta equals to 1, or already discussed this, okay? So this is a very interesting things, we need to know. And then we can discuss about the phase angle. So just now we discussed about RD. So the phase angle or phase lag. So phase lag. So when I was a student, I confused with the idea of phase lag. What's the meaning of phase lag? So why there is a so-called phase lag here? I can understand RD when I was a student. I mean, I can understand RD because it's a factor. So we know what's the effect of the factor. But what's the meaning of the phase lag? The meaning of the phase lag is that because at the design and analysis, we usually worry about maximum value, right? That's the meaning for RD. We want to know the maximum value of a system due to dynamic loading, static loading, what is the maximum. And another thing, when it's a vibrate, it's a dynamic problem. We need to know when this dynamic loading or this maximum deformation will happen, or what is the relationship between its maximum value with the loading, So this is the meaning of the phase lag. Okay, phase lag. Let's see these examples here. And the solid line. Okay, the solid line here is the response of the system. Okay, response of the system. And the dashed line here is actually the external load because it's a sine wave. Okay, it's a sine wave. So this is a sine wave. You can see this is a sine wave. So this solid line is the dynamic load of the dynamic response of the structure. You can see when for this case, omega equals to omega 1, resonance case, when the load, the dynamic reaches first peak at this time. And after several times, the structures will reach its first peak. So this duration is with so-called phase lag or time lag. because it's expressed in a phi, you can see we have a sine, it's like sine omega t minus phi, right? This is the so-called phase stack or phase angle. And if you change this slightly like t, we use t here, this is here, t, then phi divided by omega, it's like this. And the unit of this part will be time. Okay, time. So actually the phase lag or phase delay is the time, represents the delay of the displacement response of the system with respect to the excitation. In short, you apply a load to the structure. If the structure has damping, the response of the structure will be delayed, will be late than the dynamic load, will be late than the dynamic load. It's like shown here. This is for omega divided by omega and 0.5, and omega equals to 1 and 2. So it will be late, delayed to the system, to the excitation, So I explained this in English and Chinese. I understand some students from last class can speak very fluent Chinese. So I write this. This is a very important idea. So phase lag, okay, phase lag. And if we plot the phase lag, this is frequency ratio. This is a phase angle or phase lag. You can see with the increase of the frequency ratio and different damping, they have different phase angles. Okay, phase angles. So you can see this is a 0.01, this part, 0.1, 0.2, 0.5, 0.8, and 1, and 1. So different damping, and this is frequency ratio. And you can see, interestingly, no matter what damping the system has, when there's a resonance case, which means omega equals to omega n, so the phase angle between the system and the excitation is 90 degrees. Okay, it's 90 degrees. And when the damping is very small, if you still remember, for the non-damping case, it's just a 0 and suddenly change to pi, right? At the omega equals to 1, beta equals to 1 at this point. Okay. At this point, suddenly change. And this is similar, you see, this is the very small damping situation. So it changed. So this is a very important observation for any damping system. As resonance case, it's a delay of the time phase lag between the displacement of the system and the load will be 90 degree. So again, this is the importance of curves. I've mentioned several times. This is for RD, this is for phase angle. To be honest, many problems in previously, like final examination or mid examination or quiz, actually based on these two curves. So if you understand these two curves correctly, I think you can understand all these things we are discussed here in chapter 3. Okay, you understand these two curves. What's the meaning of what's the effect of the frequency ratio, effect of damping, phase lag? Then you can understand this. Okay, so we summarize this. So we have a resonance case, resonance frequency. We see omega equals to omega. We have these rules. When I give you a problem, I see the system is at resonance, which means omega equals to omega n, not omega d, but omega n. Okay. Then we have the so-called dynamic response factors. Okay, dynamic response factors. So we have all these factors. So let me show you an example. Then you can understand this more easily. We have a rotating machine with intrinsic mass. installed on block. Foundation is shown below. We have, you can see this is the load, and this is so-called foundation. This foundation, the load applied to this foundation. So vertical stiffness of the foundation, the K of this one, actually means this foundation can be simplified as STF system. So it's this value, and the vertical vibration damping ratio of this block is this value, and the mass we already know. And the rotating speed of the machine is this value, and the vertical force induced by this eccentric mass is P0 equals to 30 kilonewton. So kilonewton. So we have a question: what is the maximum vertical vibration amplitude? So what is this in Chinese? What is a maximum vertical vibration amplitude? So how we calculate this, right? How we calculate this. So how we calculate this? So you know this is a P0 sine omega t. This is a harmonic loading, right? This is a harmonic loading, and this is STF system. So if you simplify this problem, it's like this. It's actually like this. So STF system applied, subjected to a harmonic load. So we know that UST, the static loading. Okay, the static loading will be P over K. So we have this value. And the natural frequency of the system should be K divided by M, the square root. We have this value. And we know the rotating speed. So rotating speed. So we know the frequency of the external loads. So we know omega. And then with all these things, we can calculate the RD, the dynamic amplification factor. So which is 1 minus beta squared again. Then we have this value, which is 2.49. Okay, 2.49. And because you know the static load, the static deformation, the dynamic load factors, amplification factors, then you time this, you know the maximum vertical dynamic deformation. So you can calculate this. You can get this value. So this is how we use this in one way. So later we will have different ways to use this principles, ideas. STF system subject to harmonic loading. So harmonic loading. So this is this part. We have 2 or 3 minutes, 2 minutes to the break. So any questions here? This part is very important. I must warn you, if you don't understand what we're talking here, it's very difficult for you to catch up later with other chapters. Okay, good. If you don't have questions, we can move on.
Can you go back to the question, please?
Yeah, please.
I mean to the question, like just the example.
This one? Short
Yeah,
answer.
The question itself, not the answer. The question.
So I go back here.
Yeah.
Can you read one? The question about the question itself?
Yeah, I just want to read like the notice this thing.
What?
It's okay, no problem. It's okay.
Okay, no problem. That's good.
I just read, yeah.
Okay, let's take a break. 5 minutes break. It's 10:35. We'll start the